let's see. $68.
Can these problems, are you supposed to say if they converge or diverge into what? Like no.
Well, this one says use a graph of the sequence.
68.
Yes, so 68. 68 is really neat. This one, how it says. So the top is weird. Yes. You see how the top is related to the idea of a factorial, except it doesn't go by ones, it goes by twos. Yes. So this is a really, really good introduction to. And by the way, the reason that a graph would work if you do a few finite elements is because the rate at which the top and the bottom increases is not constant, but they should kind of grow at kind of like, how do I say this, proportional rates. Like a few finite elements will tell me if it looks like it's going to blow up or not. Yes? Because the top doesn't suddenly start to grow really fast after going down for a while. They just have consistent growth rates relative to each other. That's the best way I could say that. Now, 68 is going to show up later in bigger ways. Not that specific problem, but that idea. What's the bottom mean again of 68? Factorial, and that just means n times n minus 1 times n minus 2 all the way down to 1. Yes? Yeah. And a slightly better way to write it, and this is why I love that you asked this question, because we often introduce the idea of factorial, and when I say we, I mean me, and I mean I did this. And we make it sound as if there's only one way to write it. And I don't do that on purpose. Dadgummit, did I leave all my pens? Oh, I stole a pen from somebody. Neat. Okay. So n factorial, oh look at that's my blood. Okay. We normally consider n factorial to be n times n minus 1 down to 1. And do you see how that's really weird? Because depending on what n is, this could already be 1. Do you understand what I'm saying? So this captures the idea. It doesn't mean I have that many elements, and blah, 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 right? It just captures the general idea. So a different, I'm not going to say better, but it is very often better. I can write a factorial like this. I didn't have to put that in parentheses, but we're all okay. Same idea. It just starts at 1 and grows to n instead of starts at n and goes down. It actually looks cleaner. Very often I can analyze it better. I like it. So real quick, the immediate answer to your question, no, is just graph a few elements and see what it looks like it's doing. So that problem is very straightforward. We don't have to analyze it on any higher level than that. Is that cool? Yeah. But in general, I want to talk about the top now. So let me write this out. Okay. So the top, I can't rewrite it using factorial. Do you guys see how the top is related to factorial? Yeah, it's just like every odd. So it doesn't go down by 1, it goes down by 2. So I can't rewrite it with an exclamation mark. But it is related to factorial. So like, let's look at a few elements of this. A1 would be what? And this will help us figure out how to interpret this. So what is 2 times 1 minus 1? So at that point, I just have a 1. So again, when I see a definition like this, that is the uppermost term. So therefore, sometimes I won't even have 3 and 5. I'll just, in this case, I just have 1. And of course, what's 1 factorial? Holy shit. A2 is going to be 1 times 2 times 2 is 4 minus 1 is 3. over 2 factorial. Let me stop for a minute. Do you guys see? So already I've hit the first conceptual hurdle about how to deal with the top. You keep multiplying by the next thing. That's why it's like factorial. It's just not like factorial because it's not going by 1, it's going by 2. So A2 is 1 times 3, the top. A3, the top would be 1 times 3 times 5. A4, 1 times 3 times 5 times 7. Yes? So it keeps growing geometrically. I don't know if I've said that word yet. Like, not geometrically, but like, this would actually be sort of related to an exponential. But so this will be 3 over 2. A3 would be 1 times 3 times 5. And again, 2 times 3 is 6 minus 1 is 5. That's where I stop. So I stop at 5. 3 factorial. So that'd be 15 over 6, which is 5 over 2. So if you do a few of these, you'll start to capture the idea. Now, on one level, I hope you guys can step back and just analyze this. The bottom is 1, and then 1 times 2, and then 1 times 3, and then 1 times 2 times 3, and then 1 times 2 times... The top is 1 times 3, 1 times 3 times 5. So which one is growing at a quicker clip, the top or the bottom? The top. Do you guys see that? So in fact, it kind of looks like this is capturing that idea, because when this is 1 times 3, the bottom is 1 times 2, and this is 1 times 3 times 5, the bottom is 1 times 2 times 3. The bottom is always kind of like behind. Are you guys at all with me? So you could do some side work beyond just graphing this to really make sure you understand the answer you get, which is this seems to grow without bound. Okay. Maybe. So listen, factorials are trippy as shit. In later mathematics, you learn a broader way to interpret factorials that allows you to do something like take the derivative of the factorial. Do you understand why the derivative of the factorial would be remarkably weird as shit? Because the function isn't really defined fully unless I know what n is. So it's kind of like, do you guys understand? Okay, I'm sorry I went down there. Just want you to like, because in calculus, what are you guys used to? You introduce a new function and then you figure out its derivative. You look at another function, you figure out its derivative. So n factorial is a function. So then hopefully somebody's like, I wonder what this guy's derivative is. And if you think about it, that's trippy. So later we talk about a broader thing where n factorial is a specific type of this broader thing that you can actually do calculus to. Okay. Sorry, enough of that. I went way further than you needed me to for that one, but oh well. So that was number 68 in 11.1. So it's this problem here. And I just wanted you to graph some elements and see what it looks like it's doing. I really want to make this clear though. I told you last time that you cannot look at a finite number of elements of a sequence and know what it's doing unless you know broader things about it. In this case, the top and the bottom's proportional rate of growth stays the same relative to each other. So if the top is growing faster than the bottom now, it will be in the future. So then I can do that. Okay. All right, I love it. I know someone in here is going, this guy just made 1, 2, 3 hard. Okay, sorry. Yes?
I'm kind of confused about the notation, because the 1, 3, and 5, those are just examples of outputs.
So this, when I see this kind of a definition, what that tells me is I multiply a number by 2 above it, by 2 above it, up to this. So if n is 7, what's the numerator for the 7th term would stop at 13. Now what's weird is the numerator for the first term stops at 1. So the definition says start at 1, and then multiply by 2 more until you get to the maximum. And in that case, the max is 1. So I start at 1, I'm at the maximum. So that's why the first numerator is 1. So bear with me. So I'm really happy this came up because I always forget to make sure people know how to interpret this. Because I'll always get somebody tell me, A1 is 1 over stuff. A2 is 3 over stuff. I'm like, no. This is defined to be a continued product. Not just specific numbers. It's a continued product. Does everybody see that? Okay. Just like factorial, except this is one that goes by steps of 2 instead of steps of 1. Okay, I like it. Maybe. Screw you, Jeff. Okay. So like 5 factorial is 5 times 4 times, and let me do it this way. 1 times 2 times 3 times 4 times 5. Is that cool? And then we can call this 5 colon is 1 times 3 times 5 times 7 times 9. Sorry. So 5 factorial is 1 times 2 times 3 times 4 times 5. This isn't real. You with me? But if I did want to make I'd use another punctuation mark. Why not? 5 colon means 1 times 2 more until I get to the 5th number. Okay, maybe. Which explains why this goes to infinity, because the top grows quicker than the bottom. Okay, I love it. Okay. Is that okay? That's definitely trippy. So some of you guys, understandably, most stuff in 11.1 should be easy. You know it's not all going to be easy. Okay. With that in mind, anything else from homework stuff? 11.1 basically is all we've got. Okay, so what I want you guys to do, because I do too much shit. Have I bled on these? Damn it. I'm stop bleeding. So I'll use this one with my DNA on it. I want you guys to do this. Feel free to work with other people if you want to. If you don't like the look of them, then you can work alone. All right, so work on this. So basically everything we did last time.
So x equals 0 or 1. Yeah. I hate these.
Poor little things. They never asked to exist in the first place, poor little things. You're annoying. I don't know what to do with you.
Is B prod and then no times to the x. Yeah, but it's negative, so negative. Negative e to the.
Did I start you up?
Negative to the negative x. Yeah.
I did. All right, guys, let's take a look. So if I did the limit, so if I ask you whether a sequence converges or diverges, easy as shit. Just take the limit, right? Well, it just depends on if the limit gets weird or not. So again, like I said, you can bring that in. If I let n get big, this goes to 0. Sine of 0 is 0. Okay. So that does converge, and it converges to 0. Shoot. This one, trust me, somebody else did this. 2 things wrong with this. Now, real quick, if you do it the right way, you will get 0, I believe, if I did it right in my head. But 2 things wrong with that. Does anybody know what the very first, most important wrong thing is with what I just wrote?
Infinity.
I plugged infinity in. So real quick, I know some teachers maybe are more lax about it. And I'm generally a lax, kind of laid back guy. But if you're going to plug something into a function, you better be able to give it to me. So if you plug the 2 in, and I'm like, show me 2, you can show me 2 things, you can show me 2. So if you plug infinity in, you better bring infinity in the next time I see you. I want to see it. I want it to be a Pulp Fiction suitcase. You open it up, glowing. My mind melts, and you're like, well, I see in the class, everybody. But I still want to see it. I'm fine if that's the way I die, as I see infinity, that's fine. Or maybe I'll become pure energy, like Power. Okay, you ever seen the movie Power? Okay. So, bullshit. Another thing, the equally important thing is, infinity minus infinity is not necessarily zero, because these infinities were generated in different ways. So it depends on which one's getting there faster, which is why L'Hopital's rule exists. This little old medical dude said, hey, it's about the rates of things, so let me see, derivatives gotta come. All right. So how do I do this correctly then? Huh? Rewrite it, sure. As?
Natural log of the n squared plus 2 over n squared plus 2.
Yeah, properties of logs to the rescue. Okay, so trust me, if you survived Calc 1, and obviously everyone did, you had to have used properties of logs. You had to, because you did logarithmic differentiation and all this kind of logs just showed up wherever. So you have to remember your properties of logs. And now to do the same thing we did over here, I can just bring that inside, because ln is continuous on its domain. And what do I get? This should be quick, yes? The degrees are the same, so what's the limit of this? 1. And what's natural log of 1? 0. Okay, so again, it's not because the answer is 0. That's why I kind of hate that I made the first two go to 0. It's because the answer is finite. Both of those sequences converged. Is everybody with me? So if the answer would have been 7, it's convergent. If the answer would have been 18 billion to the billionth power, it's convergent. If it's oscillatory or some kind of infinity, it would have been divergent. Okay. So bad stuff, math boy. If I would have just put a cosine here, what would have been the answer? 1, it would have still been convergent. I really want to make this clear. Okay. Good job. So 4 factorial is 24. So I cannot multiply these until I know what they are. What is 3 factorial? And what is 2 factorial? 2. And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Die. So I get... How's everybody doing? Did I lose people? Sorry? 60. So I mean, never fully calculate a factorial when you're dividing parts of it out, right? Okay. Or you can if you want to. I can't tell you what to do within a certain reasonable level. How's everybody doing? You guys with me? So factorials, if you've never seen them before, they are remarkably single-minded things. And I did double check. I thought maybe there was an issue with writing like a function of n, but I didn't think there should be. So I'm not sure why the book, I don't know if I want to bring it up. Sure. Just for your own curiosity, there is a thing called a double factorial, which just means it goes down by 2 instead of down by 1. Yes? It goes down by 2. So what do you think a triple factorial might do?
Every 33.
Yeah, but do you see how that's different from this? That would be 6 factorial, and that grows stupid fast. Okay, sorry. So this stuff, don't worry about it. Only if you're curious, you can look it up. What do I do here? The ends cancel, right? Okay, all right. So what can I do? Which one is bigger? Which one's gonna have like more terms? I know they're both having. The top one has more terms. So I'm going to start expanding the top because at some point it's got to overlap with the bottom. They both kind of have 1 at the end times 2 times 3 up to, but the bottom stops earlier than the top does. I don't know if you guys are with me. So always, when I have a ratio of factorials, just expand the one that's bigger. At some point it's going to overlap with the bottom. You can cancel a bunch of terms out. So what's the top become?
And this plus 1.
And then it continues, and if it continues, I just put a factorial. And of course, then I can, and that's the answer. Cool. I like it. And if anybody's ever done any probability statistics. Sometimes you have counting methods, and this is sort of like related to combinatorics, permutations, combinatorics, blah 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 blah. If you never have, don't worry about it. So down here. Oh, no, that's okay. I'm fine. If I'm about to take, of course, how do I figure out if a function is decreasing or increasing? I just take its derivative. I was talking to a group in the back earlier. Okay, later this semester and right now, we're going to talk about like a sequence can be decreasing, and then at some point it just starts to increase forever. Is everybody with me? So you could have a sequence, and I told you to be careful about this, because you could have a sequence where the first billion terms are decreasing. So you think the function is just decreasing, but at the billionth term it turns, and it starts to increase forever. Is everybody at all with me? We've seen shit like this. What kind of thing does this? Okay, so we've seen things that do this. This is just on a bigger scale that's easier to miss because it's going to look worse, but it's fundamentally going to have this aspect to it. So, in general, when we're talking about sequences, I care what happens the bulk of the time. And in fact, in this case, the bulk of the time is an infinite amount of the time, right? So what if it's decreasing to the billionth term and then it's increasing forever after that? This little piece where it was decreasing is basically nothing. What's a billion compared to infinity? Nothing, right? So I do want to know, if it's not always increasing or decreasing, where does it stop doing one and start doing the other one? So this is very Calc 1. What's the very first thing I should do before I start doing derivatives? Yes. If you don't, I'm not going to freak out, but you really should. Then I take a derivative, and I get. And if I want to know where this thing might turn, yes, get my, what do you call them? Critical numbers. If you want to, make a little sign diagram. Do you guys see how I only give a shit about the, I don't, because where is it assumed that this starts? Because I didn't say otherwise. 1. So I really just care about what's happening. So if I investigate 1/3, if I put a number above 1/3 in, if I put 1 in, 6 minus 2 is 4, this is positive. So what's it doing forever on its domain, the sequence? Increasing. The derivative is positive everywhere that sequence exists. It's only negative where it doesn't exist, so I don't care about that. Are you guys at all with me? So that is like a 180 sign diagram kind of thing, but more targeted. I only care about that part of it. So then this one, same idea. And when I take its derivative, what do I get? Product rule, I love it. Derivative of this is -2. And then derivative of this is going to have a negative come down, so it'll be plus. How do I find this guy's critical numbers? 0. What comes out? 2e to the negative x. And what am I left? I'm going to put this first. I'm going to put x minus 1. Is this ever 0?
No.
Nope. So then when is this 0? 1. So I make a little sign diagram. If I plug in a number above 1 into this, into this, well, let's do it at this. It'll be positive times positive, so this is always increasing. Is that cool? Which makes sense, because it's 3 minus something that is getting smaller. So therefore, it's increasing. Let me stop for a minute. So chastising past Jeff in my head, because the first two I should have one that wasn't 0, and these two I should have one that starts to increase like a 3 or something. So if this would have started to increase at 3, What I would do is I would shuck off the first two elements, and then I have a sequence that's always increasing. I don't know if you guys are with me. If this started to increase at 3, I could throw the first two elements off, and then my resultant sequence always increases. Okay. All right. So what we're doing today, any questions from this before I get back into what we're going to be doing? Okay. There. Is this okay? Okay. Okay. We're about to take the next big step, and this is where things get very interesting. And I think I kind of gave this away already. I keep saying this word series, so I might as well write this down. A sequence is like elements. So like this would be 1, 1/2, 1/3. Now I kind of caught myself earlier. I was like, oh shit, I better stop and talk about what the summation symbol is. And then I'm like, holy shit, these guys know. You've all done Riemann sums. Do you guys remember the summation symbol? Yes, capital sigma. Because again, math people very creative. We're like, sum starts with S. Let's use Greek so it looks more neat. Okay. So that's literally S for sum. And if I want to sum this up, where do I start? 1, and I go to infinity. So of course, when we did Riemann sums, all an integral is an infinite number of rectangles in my sum. So it's a limit of a sum. And when you put those together, you get the big S, the elongated S symbol. That's the integral sum. And again, they went, oh, it's a large sum. Let's make it a long S. Okay. That's the drunk history of math. But it's not too far off from reality. Let me stop for a minute. Right now, is it easier for a sequence to converge, or is it easier for a series to converge?
Sequence.
Yeah, in general, it's always going to be easier for a sequence, because what's a series doing? The series would be all this shit, but instead of commas, plus signs. So in order for a series to converge, two things have to happen. So the first one is all the elements, let me see if you guys, I've said this before, all the elements can't overlap too much. And what I mean by that is, and I also say this, I say this a lot, they have to get out of their own way fast enough. So we did a series, and we're going to look at it again later, 0.1 plus 0.01 plus 0.001. That's an in-your-face explanation of what I mean by get out of its own way. That is the best a sequence can get out of its own way. What do I mean by that? Every element in this is moving over a spot. So it's literally getting out of its own way. It's not overlapping. So there's no way it can kind of like accumulate. It's just getting more and more decimal places. And that's not going to go to freaking infinity. It's going to have infinite decimal places, but we don't give a shit. That's what a repeating fraction is. So 1 repeating decimal. 1/9, who cares? Are you guys with me? 1 over n we've already talked about. In fact, we sort of did it back when we were doing improper intervals. Yes? Does anyone remember what this series does?
It converges.
Yeah, so what does this sequence do?
It converges.
It converges, yes?
Mm-hmm.
Jeff, good job, there you go. This sequence converges all day long. The series diverges. Okay, how are we doing so far? We know these two things. We know both of them. I've just never put them together. So the series we actually did back when we did improper intervals to kind of like get a little preview of this. If I add up all those terms, it's going to go to infinity. It just is. It's the weirdest thing. It goes to infinity very slowly, but so does natural log. It gets there, but it goes there very slowly. Okay. Are you guys doing okay? All right. And here's the key thing. do you see how this is? There's a sequence whose limit exists. It's convergent, but the associated series is divergent. Yes. Not only is this convergent, it converges to 0. Now let me ask you: what if I have a series, and I know the limit of this? I know it's convergent, but I know its limit is 2. Okay, stay with me now. What would that mean about the associated series? So are any elements in the sequence necessarily 2? Okay, let me see. I really need you guys with me. This first statement says that the elements in Bn, as I let them continue, approach 2. That's good old Math 180 bullshit, right? Do any elements have to be 2? No. But they have to eventually get arbitrarily close to 2, yes? Mm-hmm. So, for an infinite amount of time, the elements are arbitrarily close to 2. Are you with me? So let's assume it's approaching 2 from below. Are you with me? Mm-hmm. So like it's 0.1, 0.2, 0.3, and then it's like 1.9, 1.99, 1.999. You with me? Isn't that more than adding 1 forever eventually? If my limit is 2, aren't I gonna at some point have all my elements are bigger than 1? I really, the more you understand limits, the more you understand what I'm trying to say here. If my limit is 2, there has to be a point after which my elements are bigger than 1 forever. If you don't understand what I'm saying, you don't understand limits. If there's never a point where they're always bigger than 1, the limits can't be 2. Because then it's like, no, I'm not. I'm going to get there. No, I'm not. I'm going to get there. No, I'm not. And then it's never going to get there. If it gets there, or gets close enough, if the limit is 2, at some point they've got to be bigger than 1. If I add 1 forever, will that converge? Mm-hmm. If I add 1 forever, that's the definition of infinity. Yes? That is a definition, not the. Okay. So if, I need this to make sense. If you understand what I mean by it's got to get out of its own way, and you understand this idea that if the limit is some number other than 0, I'm effectively adding that number forever, what must be true about the sequence inside? Let me make this one. Whatever the sequence is, what must be true in order for it to possibly converge? What could the limit of the elements be? If the limit of the elements is 1/4, that's pretty small. But that means I'm effectively adding 1/4 at some point forever. If you add 1/4 forever, what are you going to get?
Infinity.
Infinity, yes? Okay. Yes, what if the limit was 1 times 10 to the negative 18 billion, Jeff, which is my favorite big number? Does everybody agree that's really tiny? If I add 10 to the negative 18 billion forever, what do I get? In frickin' infinity, yes? So what is the only thing that the limit of Cn could be in order for this to possibly converge? Yes? 0. If this limit, I need you guys with me. If this limit is not 0, then you're effectively adding whatever number it is forever, and that's always some kind of infinity. If the limit's negative 1/2, then it's going to be negative infinity. It's going to diverge. Okay. Is everybody with me? So instead of just telling you the rule, I want you to understand why the rule works. Yes? So if the limit, so here's something you know for damn sure. If I give you a series, and when I write it like this, it's understood to be this, but let me just do this for now. Obviously, I write this a lot, so if I don't put these, it's understood to be this. If the limit of AN is L not 0, what definitely happens to this? Diverges. Definitely, no question. The mistake students make is they don't understand logic. If you make an A in this class, let me see. Let's say I have a, I don't want to do this now because then you say, remember what you said? If I have a daughter and I say, I'll tell her, if you make an A in that class, I'll buy you a car. Is everybody with me? Everybody with me? I didn't say how nice of a car, but let's say she makes a B. Am I going to buy her a car?
No.
You don't know. You have no clue. You have no freaking clue. So let's focus on this for a minute. This is why. All right. First problem with today is people don't understand percentages. Second problem is they don't understand math. Third problem is they don't understand logic. So you get all these assholes on TV saying things that are logically true, and we hear them in the way they want us to. So the more you understand logic, the better everything in the universe is. If I tell my daughter, if you make an A, then I'll buy you a car. When is the only time I have to do something? If she makes an A. If she doesn't make an A, am I beholden to do anything? I could buy her a car if I want to. Listen to this one. If I go in the room next door, I will continue to breathe. So does that mean if I don't go there, I'm going to die? I can continue to breathe even if I don't go there. Yes? But if what I just said is true, I can't go in there and hold my breath. That would break my own logic. If I go in the room next door, I will continue to breathe. So if I go over there and I don't breathe, I've broken my own logic. All right, guys, is everybody with me? I need you to understand why I have to take a moment with this, because, and it's unfortunate if nobody has taken this moment, because so many theorems we see is an if-then. If P then Q does not mean that not P means not Q. Now real quick, go back to the if my daughter makes an A, I'll buy her a car. If I don't buy her a car, what happened? She didn't get an A. You know that for sure. If she gets an A, I will buy her a car. If I did not buy her a car, she must not have gotten an A. That's the totality of everything we know. If she doesn't make an A, I can still buy her a damn car if I want to. Right? Okay, maybe. Now, so if I have this, in order for this series to possibly converge, the limit has to be 0. So here's the way this is going to work. This is awesome. This chapter 11, you're going to get a bunch of series. You're going to learn a lot of tests. And it's your job is to figure out, does this series converge or does it diverge? Yes? Mm-hmm. So here's the thing. If you take the limit and it's 0, you go, shit, I got a lot more work to do. Because all you've determined, if you take the limit of the sequence elements of the series and it's 0, it could converge. You're like, damn it, now I got to know which rule, what test to apply. Are you guys, you don't even know the test yet, but that's what's going to happen. But if I take the limit and it's not 0, why is that a time to rejoice? If I take the limit of this and it's not 0, what happens? It diverges and I'm done. So guess what we call it? The creative geniuses that are mathematicians. Taking the limit of the sequence of the series elements, we call it the test for divergence. Because the test will tell you if it diverges. They're like, what do you call it? So when I give you a problem, and I say, does this converge or diverge? The first thing you do is what? Take the freaking limit. If the limit's not 0, screw it. So what do people do instead? They start attacking it with tests. And I'm like, damn it, if you would have just taken the limit, you would have seen it's not 0. You're done. You're done. You guys see what I'm saying? So we see this a lot in mathematics when I said rule out U sub. So you don't start trying to do crazy shit when actually U sub works. Same thing here. Dear God, take the limit of the elements of the series. If it's not 0, it doesn't have a chance. It's divergent. You're done. Next. Yes? So there will be some problems that are basically one-steppers. Look for those. Okay, I love it. This is really tricky for students to understand, and I don't blame you. Yes, sir.
So it can still diverge if it equals.
Hell yeah.
Okay.
In fact, we have an example.
Yeah.
What's the limit of 1 over n?
It diverges or it converges.
0. Right? More importantly, it's 0. It does converge, but more importantly, it's 0. But what does the series do?
It diverges.
Diverges. So that is a very in-your-face example of this idea. The limit being 0 means, oh, it's got a chance. And then you look at 1 over and like, you have a chance then. Oh well. You diverged. Okay, maybe. Okay. I'm try to keep myself straight because I go off on tangents. I don't know if you guys have noticed that. Oh, good. All right.
In the series
Make sure.
diverges 100% if it doesn't equal 0.
Do it again. Oh, yeah. So,
The series diverges 100% of the time. If it
Um,
doesn't, if the limit doesn't equal 0.
all right, you guys ready? Given Cn, if the limit as n goes to infinity of Cn is 3, does the sequence converge? Does the sequence converge?
Yes.
Yeah, it converges to 3. Does the series converge? Because I'm essentially adding 3 forever. No. Why test for divergence? Okay. By the test for divergence, this series does not converge. I really want you to see exactly what you just said, exactly what I said earlier. If the limit of the elements is a number, not 0, I'm effectively adding that number forever. So of course the damn thing goes to infinity, yes? It has to be 0 to have a chance to converge. Okay, maybe. Maybe if I make a big enough deal out of that. The limit of the elements of the series is 0. That means your work has just started. Not, I'm done with the problem. I get a lot of people go, the limit's 0, I'm done. The limit's 0, I'm done. That homework was easy, Jeff. I'm like, well, you did it really quickly, but you guys understand? And I don't blame you. They're so close. It's so easy to mix that up. It is. And your brain is optimistic. You're like, oh, cool. That was quick. No. Okay. All right. Let me see. Oh, good. Okay. So let's do this. What do I got? I got so much time. Too bad for you guys. So let's look at, do I want to do, yeah, okay, let me do 2 things. Let's say I have a series like this here. What you got, Jeff? So what I want to do right now, obviously, what's the matter? I won't. Obviously, does this series converge? What do you guys think? What's happening to the elements of this series? Yeah, the limit's definitely not. In fact, the limit is what? Infinity. So you're basically adding infinity to a number. You're adding really big numbers forever. So that sucker's not got a chance. But so I want to do something else for this. Can you guys tell me the first 4 sequence elements? So if this is the sequence AN, what are the first 4 sequence elements? 2. 5. 8. Slope is 3, right? So once you know 1, you know them all. You guys with me? Okay, maybe. Now I want to do this. And what the shit is this, Jeff, besides poorly written S's? Those are partial sums. So a complete sum, the whole summation symbol, means let the terms you go to approach infinity. So basically the way you can say it very quickly is add them all up forever, right? S1 just says add the first element. Okay. So who knows what S1 is? It's freaking 2, because all we have so far is one element. So S1 always equals A1. How do we get S2? So now I want to add up the first two elements. Holy shit. 15? 26. I like it. You guys with me? Okay. So those are partial sums. Okay. So what I want to do is I want to investigate a very specific kind of. So there's going to be some problems that just want this. Literally, that's it. That's all I want. And I'm going to have like one problem with test score. Just blah, 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 do this. The next level of this is sometimes you're able to figure out an expression for Sn. Do you remember when I first introduced sequences and it gave us a bunch of numbers and I said, let's figure out what the nth term is. That's An. So here I can get a bunch of partial sums and I can go, what's the nth term? So let's look at a very specific kind of sequence. Series. Well, sequence works too. So we have a geometric series. And I think I've said this word before. We had arithmetic sequences that were built on adding, subtracting. Geometric are built on multiplying, dividing. Right? And just to remind you guys, there actually is no division, so it is based on multiplication, either by a whole number or a fraction. So an example of a geometric series would be something like this here, right? That's geometric. Very quickly, that's not going to converge, right? That's a sequence, so let me be careful. Let me build up the series. Let's start with sequences. Then we'll talk about adding up the elements of a geometric sequence. But can somebody tell me what the nth term is in this sequence? What is the repeated multiplier? And we normally call it the ratio because what is the repeated? What's the multiplier? 4. And of course, we call it the ratio. We give it the letter R because if I take one term divided by the one before it, it's always the same number. So it's the ratio of one term of the sequence divided by the term before it. So in this case, R is 4. What's A1?
1.
That's crazy. And what I could do to help me out, A1 is 1, A2 is, how do I get to A2? Start at 1 and I do what?
Multiply by 4.
A3, I start at 1 and I multiply by how many 4s?
2.
2. So this is 1, this is 0. See that? I mean, that's kind of like how I can build. We did this last time. If you're having trouble coming up with an expression for the elements, try to capture how you get from the beginning to the next so you can see what part's changing. So what part of this is changing? What's the only part of this that's changing as I go? The power. So the 1 times 4 stays the same. And what's the power going to be relative to where I am? And we saw that same thing happen in the arithmetic sequence that we did, right? Okay. Because we don't start at A0, so we're always off by 1. Let me stop for a minute. So everybody, don't let this be too much. We've done this before. We just didn't do it with a multiplication defined sequence. Okay. Now, a neat question arises. This one specifically, I can tell, will not converge. Can anyone imagine a geometric series sequence that if it turned into a series would have a chance to converge? Why is this one not converged? Because what is R? 4. And I said earlier, R could actually be fractional. And one good thing with that is, instead of increasing, the elements would be decreasing, which is what we want, right?
Yeah.
If I start off positive, I want it to decrease. I need it to officially go to 0, but at least decreasing it has a better chance already. Yes? So what if I do this? 1 1/4, 1/16, 1/64. Now what is R? R is 1/4. Yes? Can anyone figure out what AN would be?
1 over.
Yeah, 1 over 4 to the n minus 1, or you can call it 4 to the 1 minus n, which is neat. But let's not do that. Let me show you a slightly better way to write this. And this is kind of neat. Let me see if you guys are with me on this. This in itself is a skill you're going to have to create, especially for these geometric series. But how can I rewrite 4 to the n minus 1? I want to have 4 to the n. How would I rewrite that so I have this as a piece of it? Does anyone know?
Over.
What do I do with the powers when I multiply two bases that are the same?
Move forward.
No.
You add them.
When I have like bases and I multiply, what do I do to the powers?
You
Add them.
So you have
So if I have 4 to the n, it should have been times 4 to the what? So I end up with n minus 1. Negative 1. So this would be 4 over 4 to the n. Let me stop for a minute. Let's check this. Are you guys at all with me? If I have 8 to the 2n minus 3, that is 8 to the 2n times 8 to the negative 3. You can always do that shit. And that happens often enough in mathematics. They should just have it as part of your tool set. Let's check this real quick. How do I check this? I know what A3 is, right? So if I throw a 3 in there, 4 to the third is 64. 4 divided by 64 is 1/16. Check. Yes? Okay. Not a bad idea to check that the damn thing you just wrote actually does what it's supposed to do. Okay. Just to go one step further, isn't this 4 times 1 over 4 to the n? That's amazing, Jeff. Ground shaking. Do you all agree with me that 1 to any power is still 1, so I could do that if I wanted to? I don't have to. But then what do? What did I just uncover? I just uncovered R, yes? Let me stop for a minute. So here is the, so already got that? So here's the general form for a geometric sequence generator. Ooh, okay, so it's basically capturing what we just figured out. Some of you guys hopefully realize that the fact we took the 4 out, probably shouldn't have done that, damn it, but we'll be okay. Because the n minus 1 would have still been there. You know, live and learn. This is the coolest freaking thing. What I want to do is I want to come up with a formula for the sum of this. Because what do you guys think about the potential for this one to converge? Remember this. What did we know about this sequence? I mean, this series? Diverges, yes? And this was 1 plus 1/2 plus 1/3. What do we know about this series? Remember we did the integral, which is actually, yeah. So that actually converges. This is 1 plus 1/4 plus 1/9. Did I miss anybody? No, okay. Now, if you look at these elements versus these elements, do you see how that's actually getting smaller faster? Okay, so there's something else hidden in there. If I have one sequence that converges and something actually gets smaller faster, it's obviously going to converge. That leads to something we're going to talk about later this semester, which is called comparison tests. But we'll get there. Okay. I don't know if you guys are still. Okay. So, here's the coolest thing. Okay, I want to remind you about one stupid little thing that'll really explain what's happening here better. Well, do I want to? Yeah, I want to do that first. Sorry, I just decided to do the other thing first. If I want to figure out the nth partial sum, what would Sn be? Well, let's see, what's A1 is A1, yes? Because when I plug a 1 in, I get R to the 0. What's A2 going to be? Times R, right? What's A3 going to be? R squared, yes? Is that cool? Up to what? Careful. Yeah, up to the nth element, which is this. Let me stop for a minute. So again, what does the S mean? Partial sum. So I wanted the sum of the first n terms. The first term is a1 r to the 0, yes? So the last sum is a1 r to the n minus 1. That's fascinating. I want a closed form for this. I don't do, if I wanted the 870th partial sum, do you want to do what this says I have to do? What does it say I have to do? Take A1, and multiply by R, add it, and then multiply by another R, add it, and then multiply by R, add it. Do you want to do that? Or do I want, I would much rather have a closed form, meaning I could just plug, what, 870 things? I just plug that number in and it spits out the answer instead of me doing all this freaking work. Okay, this is one of the coolest things. See if you guys agree. What do I get if I multiply this whole thing by R? Multiply each piece by R, what do you get? So that's A1 times R, yes? Multiply by R, what do you get? Multiply this by R, what do you get? R to the n, yes. Is that cool? Okay, this is such a trippy little thing. It kicks so much ass. It's a little tiny bit like what you have to do with E sine theta when you're doing by parts. I should have done the other thing first, but I'll be okay. If I subtract that, what do I get? I get Sn minus Rsn equals A1, these cancel, and then right before this is one of these cancel, yes? And what's the only thing left here? Minus, do you guys all see what's happening? If I subtract this minus this, these cancel. Right before this term was one of these terms, so they cancel, yes? So then I just have minus this. Yes? And what did I want? I wanted a closed form for what? For the nth partial sum, right? So if I factor Sn out, I can factor an A1 out, divide by 1 minus R, do we have a closed form for freaking the nth partial sum? Do I have a form in which, if I wanted to know what the 870th partial sum was, could I just plug 870 in and figure it out? I need you to understand. Instead of having to do this, figure it out, add it, figure that out, add it, figure that out, add it, figure that out, add it, up to 870. Yes? We're like, wait a minute, we're the humans. Holy shit, we made all this shit up. We should be able to do shit. And sure enough, I can do this neat thing and end up with what I call a closed form, which is I can just plug a value in, get an answer out. I don't know if you guys are with me at all. Maybe. This is something that shows up in some mathematics, like in some integrated mathematics courses, they do this, the sum of a geometric series. I don't know if this looks familiar to anybody. If it doesn't, you're fine. It's not like, you should know this necessarily. Okay. Let's try this out. This works no matter what, by the way. So for this thing here, let's say I want to know, so here's an example. Let's say I want to know let's just do S4. Because that's something we just do directly. If I want to know S4, what's A1? What's the first element? 1. Holy shit. And then what's R in this case? What do I keep multiplying by? 4. And then n is 4, yes? 1 minus 4. So I get 1 minus, what's 4 to the 4th? 256. So it'll be 1 minus 256 is 255. Divided by -3. You with me? And 2 plus 5 is 12 is a multiple of 3, so I know 3 goes in evenly. And that would be 85, yes?
Yeah.
What is the fourth partial sum? I got the first 4 terms, I can get the fourth partial sum, which is just the sum of the first 4 terms. So what do I get? 16 plus 4 is 20, plus 1 is 21, plus 64 is 85. So in this case, that was dumb. But what if I want to know the 28th partial sum? I don't want to do this shit. Figure out all the way to the 28th term and then add them all up? No. I'm just going to put a freaking, whatever I said, I forgot the number, 28? And do this shit, yes? All right, maybe I've got some of you on my side. And of course, some of you guys are like, I would do neither, Jeff. Well, too bad. You have to do something. Okay, maybe? So here's where things get trippy. Some of you guys, they get trippy? Can we figure out S? Now, real quick, here's what S is. S is the actual complete sum. So just an S without a number on it, holy shit, Jeff. An S without a subscript is the complete sum. It's just the same as the summation of the elements. Are you guys with me? Mm-hmm. And what that is, let's see if you guys are cool with this. What does SN mean again?
The sum of n terms.
The sum of the first n terms. So what is, can you say that phrase, but for this guy instead? This would be the sum of the first infinite terms. So what am I going to do to figure out big S here? I'm just going to let n go to, it's a limit, holy shit. So the limit, as n goes infinity, of the partial sums is equal to the complete sum. Now, my question is, when does this limit come out to be non-infinite? When does it come out to be finite? This is where things get trippy. What is 2 times 2? Times 2 is 8. Okay, so a number bigger than 1, when it multiplied by itself, will grow. What is 1 times 1? Times 1, 1. So if r is 1, that's a silly sequence. You guys agree with me? If r is 1, I get a sequence like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and that goes to infinity because I'm just adding 1 up forever. Are you guys with me? So what's got to be true about r then in order for this limit to be finite?
R has to be less than 1.
R has to be, let's be a little more technical. In order for this to be finite, the absolute value of r has to be less than 1. You're good, you're good. Because r could be negative. It could be, remember we talked about alternating series?
Oh, yeah, sure.
I want this to make sense. R is the thing I keep multiplying by. If r is 1, I never change. I diverge. If r is bigger than 1, I change. I get bigger. Diverges. If r is less than 1, what's 0.9 times 0.9? 0.81. Yes? What's 0.81 times 0.9? 0.729 times 0.9 is 0.6, blah, blah, blah. I'm getting smaller, so whenever I multiply a number by itself that's between 0 and 1, or between negative 1 and 1, really, the result is smaller, yes? Let that make sense. In order for this to converge, in fact, if r is less than 1, what happens to this? As n gets really big, what 0.9 to the 8 billion? Do you understand that it's basically 0? So as long as this is true, this goes to 0, in which case this sum is actually directly equal to this.
That's where it comes from.
That is where it comes from. Now listen, there's going to be a lot of series that we can say it converges, but we have no way to figure out what it converges to. you're gonna have to know that, and just let that be true. It was really not satisfying to me as a student. I'm like, but what does it converge to? And they're like, we don't know. Damn it! All right. It always troubled me. But of course there's series we don't know what they converge to because there's no way to write Sn. If I can write Sn, I can do the limit. And then I can figure out what it converges to. Can I always write Sn? No. In fact, I know I'm throwing a lot at you. Okay. I will do an example like this, a concrete example, but before I get there, if I have this series and I try to write Sn, you can't. Can't be done. Not that it's too hard for us. Not that, ooh, you don't know yet. But I don't give a shit who you are. You can't do it. You can write enough to see that it goes to infinity, but you cannot write a closed form for it. Do you guys understand what I'm saying? Maybe. This is a closed form for this, for Sn. This is a closed form for Sn, yes? I cannot do that for this series. And if I can't do it for some series, I can't take the limit, I can't figure out what it actually converges to. And that's just something I gotta live with. You're good, okay. So let's do a concrete example. Oh, I got time. I can calm down. Let's do a sorry. There's so much, and I'm really sorry if I go on too many tangents, but there's so many cool things. As a student, I know you're like, what's my homework gonna look like? I don't care about this other shit. Okay, sorry. So let's try a concrete example. Let's do that one we just did, this one instead. Let's say that I have this. You could do it, Jeff. So here R was 1/4, right? We had that earlier. So what does this, if this is AN, what does this equal? Well, I know in general this equals A1 over 1 minus R, yes? Oh, real quick, why does that work? Because the absolute value of R is less than 1. So if it's like 817 over 818, good. If it's 818 over 817, no. Okay. So now I can plug my specific information in. What's A1? Good, the first element is 1. R was 1/4. So 1 over 3/4 is 4/3. That is cool. Now that's satisfying, right? You're like, I got this series, I add them up, I know it converges, and I know what it converges to. Oh man, that's good. Just doing a lot of cases, you're like, I got this series, I know it converges, I have no freaking clue what it converges. Oh well, too bad, go to the next one. That's the way it is. Okay, maybe. By the way, I might as well say this right now before I forget. In the homework, they do talk about this. And they actually tell you what it converges to. Mm-hmm. Have you guys gotten there yet? Do you guys remember what it converged to? Yeah. Once we get into chapter 11, let me think, where is it? Oh yeah, we got to get to Taylor series. I might post this in Canvas before that. But once we get to Taylor series, which is 11.9, 11.10, then I'm going to talk about the proof of this. Because you're like, the first thing you should say is, why is pi there? All right, I'm sorry. So this is an example. Like, I can't do this. I can't write a closed form for it. I think they proved with this, but I can't remember. But this one, he figured out what it was. In a very creative way. A little cheers for him, you know. He did too many. Euler did. It's like, leave shit for other people, man. Okay. So right now, you have to know this. You have to know this. And you have to know this if R is less than 1. Okay. Geometric series happens often enough in the natural world, in observations we make. We have to know how to work with it. Have I said enough yet? Yes, I've said enough. So I want to let you guys work on this. Blah, 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 blah. Okay, good.
How did we discover the proof for this?
Oh, for that?
Yeah.
Oh, dude. I think historically it was sort of tangential to something else he was working on.
Mhm.
He was looking at Taylor series for sine and stuff, and
Yeah.
if I remember correctly, it was just sort of, he wasn't specifically looking for that.
It was just a coincidence.
Yes, he just noticed
Yes, dude.
things about it, because, and that's if my memory serves. I'm pretty sure that's right. So the side that says 11.2, that's what we just talked about. Try those out. There's like two sets of three problems, right? So try those two sets of three problems out. This one's really neat. It's related to something we already did, and you're gonna get the same answer we got before. And then I'll point it out. So somebody did notice that this is geometric, but you don't have to notice that. So like A1, A2, A3, what did I say, 5? Of course I did. So A1 is
10. Oh, wait, 10. Wait.
A1 is 1/2. A2 is crazy. 32. And then S1 would be 1/2. S2 would be 3/4. S3 would be 7/8. S4 is 15/16. And I mean, if you look at it, could you tell me an estimate for, or just tell me what you think the S is, the whole sum? What does it look like those are approaching? They're approaching 1, it looks like. In fact, did anyone get SN? Who didn't notice it was geometric? So we're going to compare it to what you get for geometric. And we get SN. Look at the bottoms. How do they compare to where I am? 4 versus 2, 8 versus 3, 16 versus 4. Especially considering where it came from. What's 2 to the first? 2. What's 2 squared? 4. What's 2 cubed? 2 to the fourth. So what's the bottom always? 2 to the end. And how does the top always relate to the bottom? Now this is a really good general thing we just noticed. If you could just look at it, before you do shit, you're like, oh, the top is always 1 less than the bottom. If you get an expression for the bottom, the top is that minus 1. You already know that. So you don't have to waste time on the top. It's just whatever the shit the bottom is, minus 1. We know that from the beginning. You guys see that? You want to look for that, like, higher level, just, what do they call it, 5,000 foot? We just look at it and go, oh, I see that, and just keep it in mind. If I realize this is geometric, do you guys see why this is geometric? No, screw you, Jeff. I can rewrite this like this. And let me be even more specific here. What's the one thing that's kind of off here? What was the general form of a geometric supposed to have here? We could do this. You don't have to do what I'm about to do, but I want to show you. What's the general form for a geometric? And what do I have here? Okay, so if I wanted to force it, Can you already tell what R is?
Yeah.
And do you already know what the first term is?
Yeah.
So what I'm about to do is unnecessary, but I want to just show you can do it if you want to. If you pull a 1/2 out, how many 1/2s are left? Take 1/1/2 away, how many are left? N minus 1, yes? Now is it in the form A1 times R to the N minus 1? Did I need that help? Because I already knew what A1 was, yes? I already knew what R was. Did I need to do this? But if you want to for yourself, I've noticed people like it when it's perfectly in the way it's supposed to be. You could do that shit. So, just to recover what we got here, who's got the SN formula in general? No. For SN, sorry.
A1, 1 minus R to the power, then over 1 minus R.
Good. Okay. So see, we recover what we just got up here. It better be the same, or we can throw this all out and leave. A1 was 1/2. R is 1/2. R is 1/2. So I get 1/2. 1 minus 1/2 to the N over 1/2. The 1/2s cancel. I get 1 minus 1/2 to the N, which is 1 minus 1 over 2 to the N, which is 2 to the N minus 1 over 2 to the N, making LCDs, which is the same thing we got up here. What about? Okay. I love it. So I love that you notice it was geometric. You kind of have shortcuts then to kind of use if you want to. My intention was for you to create it yourself, but yeah. Is everybody semi with me? All right. How are we doing with number 2? You guys on number 2 yet?
You split them up into 2 series.
Yeah. This is an example of a specific thing that can happen with series. If you write out, here's what's funny. Do you notice how I just said find the first 5 partial sums? And do you notice over here I wrote A1, A2, A3? I didn't have to do that shit. S1 is the first term, yes? And let me see, the first term would be 1/2 minus 1/4. Is that cool? S2 would be that plus the next term. And what's the next term when you plug a 2 in? 1/4 minus.
1/8.
Do you guys see what's going to happen here? Is that cool? Do you guys see that? So these would go away and it kind of collapses to just be the first and last so far. Do you guys see that? Okay, maybe. These have a very specific look to them. Very specific look to them. It doesn't have to be 1 over 2 to the N, but it's kind of like a difference of 2 fractions where the fractions overlap as you go. This is so cool. If I have like a thing and I push it and it kind of like fits into itself and then it becomes this little thing so I can pull it back out like a telescope, yes? So you're not going to believe this. We call this a telescoping series. Do you see how the middle collapses and the end, top and the bottom kind of come up and join together just like a telescope? What's going on there? Yes? Maybe. Screw you, Jeff. So S2 would be 1/2 minus 1/8 is. That's right, kids. 3 is. And then 1/4. S3 would be, if I continue this idea, it'd be 1/2 minus something plus something, minus 1/8 plus 1/8, minus 1/16. I could just kind of go straight to the bottom of the telescope, yes? Okay, I just keep buying the next upgrade to my telescope. It just gets longer and longer so I can see further. Okay. I've got one piece of my head I'm watching. What's 1/2 minus 1/16? Huh? No, 1/2 minus 1/16? 7/16? Okay. And then S4 would be 1/2 minus, I don't know if you guys are really with me on this. Are you guys with me? It'd be minus 1/4 plus 1/4, minus 1/8 plus 1/8, minus 1/16 plus 1/16, minus 1 over 32.
31, 30 seconds.
Sorry?
31, 30 seconds. Or sorry, 15, 30 seconds.
Yeah, there we go. 15, 30 seconds.
On to the next one. 30.
You're good, you're good. And then S5, did we get S5 yet? It'll be 1/2 minus 1/64. Yeah, what is that? It'll be, you know better than me, 31/64?
Yes.
Yeah, Jeff. Do you guys see the relationship here? The bottom, for the first term, the bottom's 1. For the second, it's 8. For the third, it's 16. So the bottoms are all powers of 2, but it's just how are they offset from where they are. So I know the bottom has a 2 to the n, but 2 to the 1 is not 4, so it must be 2 to the n plus 1. Yes, do you guys see that? You look where you are and what it is. You can tell they're like powers of 2, but you have to adjust it because they're not perfect. At the first one, it's 4. So Sn must be 2. I forgot what I just said. The bottom is 2 to the n minus 1. Plus 1. And then the top, what's the top going to be? Do you guys see what's happening on the top? 1, 3, 7, 15, 31. It's always 1 less than some power of 2, yes? So it'll be 2 to the n. And let's be careful. So if 2 to the n, this would be 2 minus 1. So 2 to the n minus 1 looks like it works. 2 squared minus 1 is 3. 2 cubed minus 1 is 7. Okay. So exciting, Jeff. Okay, maybe. Now, I'm pretty sure this one you can't find Sn. So don't pull your hair out over it. All right. One last one I want to do real quick so don't worry, we'll do this next time, but I just want to do this real quick. Can anyone tell me what R is? 1/10. This is definitely geometric. That's probably why it's here. Will this converge? Yes, this is less than 1. And so what does it converge to? S would be, A1 over 1 minus R. A1 is what? Be really careful. A1 is 1/10 over 1 minus 1/10. 1/10 over 9/10. The 10s cancel, you get 1/9, which if you remember, this is just 0.1 plus 0.01 plus 0.001, which is the first example I gave you guys. And we got freaking 1/9 for the answer before, so we better get 1/9 for the answer now. Just a more concrete way to do it. Okay. I think it's enough for today. What do you guys think? Is that enough? Okay. Get out of here. We'll finish this up next time. We'll continue our way to chapter 11. If I remember, somebody reminds me, maybe I can put that. It's called the Basel problem, Euler-Basel problem. The 1 over n squared becomes pi squared over 6.
From my understanding, apparently he found out for every even p, which is stupid.
What do you mean?
So Euler didn't just found out 1 over n squared, he found 1 over n fourth. But
He
for
found-
every n p, but we don't know what the odd p's are. It's so stupid, isn't it?
There could be a way, who knows?
I know.
Just nobody's figured it out yet.
So crazy.
Which is trippy to me. At one point you're like, well, if they didn't figure it out, how the hell would I? But we're standing on the shoulders of giants, so there's like so many things left to be discovered.
We
It's
got
crazy.
computers too, and
Yeah.
we still can't find it.
Yeah. Which, it could be, the reality could be, it's impossible. That could be the reality.
That could.
Which, I'm cool with. I don't want to know everything.